Hey guys, here's section 8.1, the vector and parametric equations of a line in a plane. All right, so just please go through this tonight, and then the homework will be at the end, and try that for tomorrow. So we're going to start back in grade 9 when we were talking about a line, because that's what we're doing today, lines. So if I were to ask you what are the two properties of a line, now you might not have talked about it this way, and I know if you're in my class, we have talked about it. But can you remember what the two properties of a line are? And of course, if you said position and direction, you're correct. Right? So the two properties of a line are position and direction. Right, a line is located at a certain place or a certain position, and it's going in a particular direction. Right? One thing it doesn't have, like a vector, is magnitude. A line has no length. Right? It goes on forever in both directions. So how did we represent these in grade 9? Well, position we gave as a point. All you need to know is one point on the line to know where it's located. And a lot of times we use the y-intercept in y equals mx plus b form. But the position we gave as a point, and the direction was slope. So we said that a line started in a particular place or is located in a particular place and was going in a particular direction. That was enough information to tell us everything we needed to know about the line. So what we're going to do now is, instead of talk about slope and y-intercept to describe the line, we're going to use vectors to describe the line. So let's think about this question right now. Imagine that you're running in a straight line, right? So let's say we start here, and we start running, say, that way. Your position along that line changes as what changes? And what we're looking for here is time. Right? As time goes on, your position changes. So if we start somewhere and run for a particular length of time, we'll be able to get to anywhere else on that line. Right? If we run for a short time, we can get to that point. A longer time, we can get here. A longer one here. If we run for negative time, which doesn't make sense in the running scenario, but if we back time up, we can actually go the other direction, right? So basically, if we start at a point and run in a direction a certain amount of time, we can get to anywhere else on that line. So that's kind of introducing how we're going to bring vectors into this. Now let's say you have your starting position and your direction. We could give our starting position as a point, just like we did in grade 9. So if we have a point, we know the location of our line, or at least the location of one point on our line. And then if we couple that with our direction, we can get to any other point on the line. So we could give our direction here as a what? So what have we been using to describe directions here in this course? And it's a vector, right? We can, instead of using slope, we can now use a vector to describe direction. And so the parameter t will represent how much, quote, time has passed, or how many times we go that direction vector. All right, so if we have a point on the line, let's call it p naught, meaning just our starting point, and then we have a vector that's in the same direction as our line, we can just go however many direction vectors starting at point P, and we can get to any other point on that line. So here we'll say that P naught will have the coordinates x naught, y naught. We're doing this in 2 dimensions today. And let's say our direction vector has coordinates a, b. These are these are algebraic vectors, because we're going to be doing this on our Cartesian plane, just like we did in grade 9, right? We're going to graph these lines on a Cartesian plane. And then any point in general we'll call P, and that'll be x, y. That can be any point on the line. Just like in y equals mx plus b, remember we said y and x represent any point on the line. Here the point P, x, y is any point on the line. P naught, which is x naught, y naught, and that just means starting values. the starting P and the starting X and Y, that's a particular point on the line, and AB is the direction, or the direction vector for the line. So we can now define what we call the parametric equations of a straight line and a plane. So as you noticed from the previous slide, XY was any point on the line, right? So what we're saying here is you get any point on the line by starting at your initial X value, going A, remember A was the X component of the direction vector, T, which is however many times. Right? Y is the Y coordinate of any point on the line. You start at a Y coordinate and go B times the parameter T, meaning you start at the initial Y value, and however many times, that's T, you go the Y component of the direction vector. We'll do some examples here so you'll see. But this is the parametric equation. And again, from the previous slide, you can see the XY, which is P, the X naught, Y naught, which is P naught, and the AB, which is the direction vector. So now we can have a question like this, right? Just like in grade 9, we have 2 points that are given to us, and we want to find the equation of the line through those 2 points. So we're not going to do y equals mx plus b, but we're going to do now the parametric form of the equation of a line in 2 dimensions. So again, we have our line, which let's say looks like this, just for argument's sake. I'm not drawing this to scale or anything, but let's say there's our line. And our line goes forever in both directions, and it's got 2 points on it. Let's say there's A and B. So what we need then is we need a P naught, or a particular point on the line to start. We need any point on the line. Now, we could make it A or B. It doesn't matter. Let's make it A for argument's sake here. So let's say it's A. We could have made it B, it doesn't matter. Now we need a direction vector, right? So our direction vector is going to be a vector that is parallel to the line, or going in the same direction as the line. Now in this case, since we have 2 points, we could just use the direction vector AB, right? So AB, that vector, would be a really good direction vector for this line. It would describe the direction perfectly. So here, our direction vector AB, again, is going to be -1 minus 2, so that's the x coordinate of B minus the x coordinate of A, and 12 minus 5, or the y coordinate of B minus the y coordinate of A, which is -3, 7. So now, we have our direction vector, and we have our P naught, or our starting point. So we can now make the parametric equations for this line. Remembering that the parametric equations are x equals x naught plus AT, and y equals y naught plus BT. So just like in y equals mx plus b form, we leave the x and y, right? Because they represent any point on the line. Now we know the x coordinate of our P naught is 2, and the y coordinate is 5, plus A. A is the x portion of our direction vector, so that's -3. So yeah, I'll put in plus -3, or we can just say minus 3. T is our parameter, and 5 plus our y component of our direction vector, T. And that is then the parametric form. Now note, we could have many parametric forms. Right here it asks for 2 of them. It's not like y equals mx plus b, where if you write the slope in lowest terms, everyone's going to have the same slope, and there's only one y-intercept. Here we can use any point we want and any direction vector we want. So for this one, for example, we said P naught, again, was 2, 5, and our direction vector was -3, 7. We could, if we wanted to, say, well, let's make p naught, let's make that b instead, right? So that's negative 1, 12. And let's make our direction vector. We can make it anything we want, but let's make it the negative version of our other direction vector. Let's make it going the other way instead. So we could say 3, negative 7. Now remember, because that vector is a scalar multiple of the other one, they're collinear, right? Any vector, two vectors that are scalar multiples are collinear. So we could have used negative 6, 14. We could have used negative 21. Negative 21, 49, right? Multiplying it by 7. We could have used 9, negative 21, multiplying it by negative 3. Anything that was a scalar multiple would have been fine for that direction vector. So we could now say that x is negative 1 plus 3t, or y is 12 minus 7t. Both of these are parametric equations of the exact same line, right? As long as you have a point that lies on the line and a direction vector that's parallel to the line, it represents the same line. All right? There is also another form of the equation of a line in 2 dimensions, and this is the vector equation. Now notice it's got all the same components. It's got your xy, which is the position vector of any point on the line. It's got your x naught, y naught, which is the position vector of a particular point on the line, or p naught. It's got ab, which is the direction vector, and it's got your parameter t. But instead of writing it as 2 separate equations with the x and y components, it simply writes it as 1, right? So this is the vector equation because these are all vectors, right? Right, xy is the position vector of any point. X naught, y naught is position vector of a particular point, and AB is the direction vector. So all of these are vectors. So if you look at it, they have the same variables. Everything is the same as parametric. It's just written differently. Instead of each x and y component separately, like I said, it's all together as vectors. So now we can look at an example like this. It says a line passes through 3, negative 2, and has a slope of negative 4, 5. Write a vector equation for this line. So now we're given information like we would have been in grade 9, but now we have to do vector equations. So again, when you always say to yourself, I need position and direction. Okay, position is a point. Now in this case, we do have a point. It says p naught is going to be 3, negative 2. So x naught, y naught is 3, negative 2. Now, it gives us a slope of negative 4, 5. And again, slope is rise over run. So here, remember, that's delta y over delta x, or the change in y's over the change in x's. So just to look at quickly here, if we had a slope of negative 4 over 5, it means we're going to drop 4 as we go over 5, right? So we go down 4 as we go over 5. So if we were to say that, well, let's pretend that this is the origin, just for argument's sake here. And so I'll draw a set of axes here just to show that we have a vector. So this vector then, you'd say, well, what's the end point of the vector? Well, it's 5, negative 4, right? Because we go 5 in the x direction and 4 down or negatively in the y direction. So that corresponds to a direction vector of 5, negative 4. All right, so again, because the slope has the x part on the bottom and the y part on the top, or the difference in y's on top, difference in x's on the bottom, and the point has the x's first and the y's second, right? So the end point of that vector is going to be 5, negative 4. So the position vector here, or the direction vector, will be 5, negative 4. All right, so that gives a vector equation of, again, xy, because that is any point on the line, equals our particular point, or the position vector of our particular point, which is 3, negative 2, plus our direction vector, which is 5, negative 4, t. So that then is our vector equation of this line. Now, what is the point that corresponds to t equals 3? So remember, because 5, negative 4 is our direction vector, we're multiplying it by a scalar, so we can go any scalar multiple of that vector we want. Right? The bigger it is, the farther along we go along the line. So let's start at 3, negative 2 and go 3 direction vectors and see where that takes us. So t equals 3. So yeah, in our equation, we're going to set t equal to 3, and we're going to write xy is 3, negative 2 plus 5, negative 4 times 3. And normally we write that 3 out in front, right, when we're doing a scalar. So I'm going to write it out in front. So now we have xy is 3, negative 2 plus, we just multiply that vector by the scalar. So that's going to be 15, negative 12. And then we just adjust the screen there. Say, well, that means our point xy is going to be, we add those two vectors, so 18, negative 14. So when t is 3, that is the point on the line that is corresponding. So we just set t equal to 3, and then do our vector arithmetic like we know how to do, how to add scalar multiplication and all that. So now we can do questions like you would have seen in grade 9, where we'll ask, is this particular point on the line? So in this case, what we're going to want to do is actually write this as the parametric form again, right? So remember, to go from vector to parametric, we're just writing the components separately. So x here will be 3 plus 5t, right? X is 3 plus 5t there. And then y is negative 2 minus 4t. And now we can plug in 19, negative 22 into those equations and see if we get the same t value. Because if we get the same t value, then we know that if we put that t value into the vector equation, we're going to get to that point, which means it's on the line. So let's sub into both of them. So sub x is 19, and then sub y is negative 22. So if we do that, we get 19 is equal to 3 plus 5t. Solving that, we'll get 16, subtracting 3 from both sides. Dividing both sides by 5, we'll get t is 16 fifths. In the y equation, we'll put negative 22 equals negative 2 minus 4t. We can add 2 to both sides to get negative 20 equals negative 4t. Divide both sides by negative 4. Get t is equal to 5. So what we notice here is that it is not. They are not on the same line. Right? The point is not on the line because we have the t values are different. If the t values were the same, it would have been considered on the line. So now we can write the equation y equals mx plus b form. But let's do it a little bit differently again because we have vectors. Right? So if we have our vector equation, again, of x, y is 3, negative 2, plus 5, negative 4, t, and you say, well, we already know the slope, right? The slope is negative 4/5. It was given to us in the question. So let's just note that. And again, it's delta y over delta x, and remembering this is the y component of the direction vector, and that's the x component. So negative 4/5. So then, all we need is the y-intercept. So what we need to note then is that for every y-intercept, the x-coordinate is 0. So what we can do is, again, if we take those parametric forms, x equals 3 plus 5t, and y equals negative 2 minus 4t, and in the x equation, we can set x equal to 0 because we know that that's what's going to happen. Right? We know that every y-intercept has an x-coordinate of 0. So we'll do that and say 0 is 3 plus 5t. And we'll solve that to get t is negative 3/5. So once we know that t is negative 3/5, we sub that into y. In y equals negative 2 minus 4t. So when we do that, we get negative, or sorry, pardon me, we get y is negative 2 minus 4 times negative 3/5. So looking ahead a little bit, I know I'm going to need a common denominator of 5. So negative 2 is negative 10 over 5, then plus 12 over 5. So the y here is 2/5, which ends up being our y-intercept, because we know when t is negative 3/5, our x-coordinate is going to be 0. So when t is negative 3/5, our y-coordinate will be 2/5, and then that is our y-intercept, or our b value. So we can then go ahead and write our equation as y is negative 4/5 x plus 2/5. One of the nice things now about using vectors instead of slopes to talk about directions is that we can talk about vertical lines a little differently. Because remember before, the slope of a vertical line was undefined because the delta x was 0, right? There's no change in the x values in points on a vertical line. So we'd be dividing by 0. It's undefined. We can't have a slope for that. But when we use vectors, we can, right? Because we can talk about what is a vector that is parallel to a vertical line. And if we note that the vertical axis is parallel to a vertical line, and note that, well, that's just the unit vector we could use that's parallel to the y-axis, which is the vector j. So the vector j here, remember the vector j is 0, 1, but it is a vector that's parallel to the y-axis. So because it's parallel to the y-axis, it's parallel to any vertical line, which means we can use it as a direction vector now for any vertical line. So where before we couldn't have an equation y equals mx plus b form of a vertical line because the slope was undefined, we can now talk about an equation, a vector or parametric equation of a vertical line, no problem, because the fact that the delta x is 0 isn't bad here. It doesn't mean we're dividing by 0. It just means the x-coordinate of our direction vector is 0. So here we could have xy is our point, which is 2, 3, a particular point, plus 0, 1, t. And now that's a vertical line, and we can write its equation just like anything else. So this question asks us to determine vector and parametric equations for a line that is perpendicular to r 3, 5 plus t 1, negative 2, and passes through the point negative 1, negative 3. So if we have this vector, now we've been using the xy. You'll also see r vector, that's just a position vector of any point on the line. Either way. So here we have our is equal to 3, 5 plus t times 1, negative 2, where t is any real number. All right, because it's the parameter. So we also need it to be through the point 1, 3. So note that in our equation here, our direction vector is 1, negative 2. So if we want the direction vector of a perpendicular line, we want a vector that, when dotted with this vector, will give us 0. So let's say we had another direction vector, d2, and if we wanted d2 to be perpendicular to d, we want it to be 0 when we dot them. So what is a vector that when we dot with 1, negative 2 gives us 0? And the quick way to do this is just switch the coordinates and change one of the signs, right? We've talked about this before. So when you do this, you are going to get 2 minus 2 or 0, and because when you dot the vectors, you get 0, that means the direction vector for our new line, which I just called d2, is 2, 1, because it's perpendicular to the original one. Combine that with the fact that our new p0, or our new point, particular point on the line is 1, negative 1, negative 3. We can now write our new equation as r is negative 1, negative 3 plus t times 2, 1, where t is any real number. I don't think I've been writing that part, but it is important to write t is any real number. It's a real scalar. So that's it for this lesson. All right, please try this homework and come prepared tomorrow to take up questions.